Good afternoon, at least on Eastern and Mountain Time where we are, and welcome to week 3 of the LambdaConf 2020 Global Edition. With us this week, we have Morgan Thomas, and he's going to be speaking on his library called Streamly. Just in case nobody read his bio, Morgan is a software engineer. He's been working professionally with Haskell for the last several years. Morgan has a background in math and philosophy and is very interested in programming theory. So I hope everybody's excited as I am to listen to this great talk from Morgan. And we're going to just pause probably for a couple of seconds here until we have a few more people online, and then we will have Morgan start. Morgan, thank you for being with us today. We're really excited to have you for our week 3 event.
Well, thank you guys for coming to listen to my talk. I'm really excited to be here and share this information with you. However, I can't take credit for this library, Streamly. That's actually, the credit goes to Harendra Kumar, but I'm going to show some tips and tricks from my experience for making all these pieces I've mentioned here work together in a way that's good.
So, and just in case anybody's wondering, we will have a question and answer section at the end. There should be something at the bottom of your screen that allows you to ask questions, and we will take those at the end. All right, I think we are ready to go.
All right. Okay, so what are we talking about here? So doing concurrency in Haskell. I'm going to start from like the very basics here of concurrent programming. Likely a lot of you will already know a lot of these things. I don't want to assume. Okay, let's talk about what is concurrency and what is parallelism. How are they different? Because they are closely related. So concurrency is when you're doing 2 or more things, not necessarily exactly at the same time, but they overlap in time intervals, like one starts before the other finishes or something like that. That's concurrency, right? And parallelism is doing 2 or more things at the exact same time. So you can have concurrency without parallelism, like when you have a single processor that's doing some task, and before it finishes the task, it switches to doing some other task, and then maybe that task finishes or maybe it doesn't, but in any case, it goes back to working on the first task. That would be an example of concurrency, which is not parallel. So if you have concurrency, you might or might not have parallelism. If you have parallelism, then you do have concurrency. And you also have either multiple computers or you have a multi-core computer, which most of us do. Here's on a hardware level, sort of the very basics of what's going on when you have concurrency and parallelism in a typical like CPU-based context, right? There's also like GPUs and stuff like that that we're not going to get into. But if you're doing it in a CPU, you've got multiple cores. Each of these cores is essentially a computer in itself. It can execute a pipeline of instructions, right? A program. It can execute multiple tasks, not at the same time, but by switching between them using a task scheduler built into the operating system or something like that. And then they all talk to the same RAM, the same random access memory, which is going to become an important point in a moment. So let me scope this talk real quick. So we're only looking at Haskell, and we're looking at concurrency with the potential for parallelism. And specifically methods that are good for applications where you've got some kind of like real-time data streams coming in, and you need to do stuff with them as the data's coming in. So like, a lot of web services fit into this kind of paradigm. And I'm going to tell you about 3 methods that can help in architecting this kind of system. We're going to look at MVars, which you can use for synchronizing tasks between threads that are concurrently cooperating on something. We're going to look at software transactional memory, and we're going to look at composable streams. And if you don't know what those are, that's fine. I'm going to talk about it. And so things I'm not going to talk about that are also very important in concurrency and parallelism. In Haskell, there are ways of making computations implicitly multi-threaded, where you yourself the programmer, don't see or work with the threads. You've got sparks. I'm not going to talk about that. I'm not going to talk about using GPUs, which can do many, many things at once. I'm not going to talk about SIMD parallelism or distributed computing. These things are important, but definitely don't have time to talk about them. Some terminology real quick. We've got, so a process, right? Just a running instance of a program. You run your GHC, you got an executable file, run it, that's a process. Making a process is pretty expensive. OS threads, each process is going to have 1 or more operating system threads, which is a part of the process, which is like one sequential task where the process could potentially consist of multiple of those. So OS threads allow for that by, you know, the operating system will look at, okay, how many threads are running and all the processes, how many CPUs are there, and tries to schedule time for each of them on the various cores. So it's like time sharing, right? I'll give you a slice of the CPU, and then when you're done, I'll give the CPU to some other thread for a slice of time. And these OS threads are pretty expensive to create. You probably don't want to have millions of them going at once. Haskell threads, very similar to threads. It's like a unit of sequential processing in a Haskell program, and the different threads in a program run concurrently. And this doesn't use the OS task scheduler. It uses the Haskell runtime system, which will schedule the Haskell threads into a potentially smaller number of OS threads. The number of OS threads is set by a command line argument that you pass to your executable. So for example, you might set the number of OS threads to the number of cores. And since each Haskell thread is, relatively speaking, very inexpensive, you can have lots and lots of Haskell threads and a small number of OS threads. And that can be a nice way to structure a program. Okay, so when I just use the term thread in this talk, I'm just going to mean a Haskell thread, just so that's clear. And then if you haven't heard of race conditions, we're going to be talking a lot about them. It's a type of bug in concurrent software where things don't happen in an order you expected and the result is wrong. So that's obviously very broad. We'll look at some examples and how to avoid these race conditions. So let's talk about why concurrent programming is hard. So you've got multiple threads that are all doing their own thing at their own pace. You don't know exactly what order things are happening in. There's like a scheduling algorithm that's going on where you don't know exactly how it's going to schedule things. And furthermore, these threads have to communicate with each other, right? They have to share information in order to be able to work on a task together. And the way this happens on a hardware level is they have access to the same RAM, right? You remember I showed you this graph, right? So core 1, 2, 3, 4, they're all accessing the same RAM through the same memory bus. And that's how they're able to communicate, right? One thread writes to a chunk of memory, and then another thread reads it. That's how they communicate. There are other ways, but that's all I'm going to talk about as far as ways for threads to communicate. Right, this means like you can, I should say, you can attempt to read and write the same spot in RAM from multiple threads at the same time. And there are various invalid things that can happen when it's possible for you to do that. So here's an example. So in this example, we've got a variable x, which starts out with the value 1. This is just some location in memory that has a number. And we've got 2 threads. And let's say these threads are both started at the same time. Thread A sets x to 3, and thread B increments whatever number is at that memory location. So depending on exactly what order things happen in, these 2 threads starting at the same time could produce 3 different results. So here's one thing that could happen, right? So thread B consists of 2 steps, or well, 3 steps really, right? So first it reads x from memory, and then it increments the number it read, and then it writes that back to the same location. So one thing that could happen, first thing that happens, thread B reads x, and then adds 1, writes the result. So now x is 2, and then thread A overwrites that with 3. That's one thing that could happen. Or here's another thing that could happen. First, this thread A writes 3, and then thread B reads 3 and adds 1 and writes 4. That's another thing that could happen. So x could end up being 3, x could end up being 4. Or here's another funky thing that could happen. Maybe the first thing that happens is thread B reads x from memory, so it gets 1, and then the task scheduler pauses thread B, starts executing thread A, writes 3 to x, and then thread B writes 1 plus the number it read to x. So now x is 2. So like, this doesn't make any sense, right? This program doesn't work. We can't predict what it's going to do. So this is a typical example of the kind of problem that you run into with multi-threaded programming, and it's a race condition, right? Depending on the order things happen in, which you don't have exact control over, different results will occur. So how do we avoid race conditions? You don't want to just like read and write whatever memory you want to, whenever you want to, when you're writing a multi-threaded program. If the memory is shared with some other thread, the results might be invalid. So you need to think carefully about how you're writing memory and reading memory whenever it's shared between threads. Here are some software architecture design patterns I'm going to talk about for dealing with this. We can use pure functions, and those ensure that we never write to memory, which another thread is trying to read, when we're doing a pure function, right? That never happens because pure functions don't write to memory that represents an object that's referenced somewhere, right? So that just rules out this kind of problem immediately. But you can't use pure functions for everything. Yeah, we're going to talk about MVars, which are variables you can use for synchronizing work between threads, so it happens in a proper order. Software transactional memory is for having shared memory like that variable x, but using it in a way where it can't produce invalid results due to a race condition. Talk about how that works. And then streaming, which when you have like a lot of things going on in a concurrent program, streams can be a nice abstraction to sort of assemble everything together without race conditions or the other kind of concurrency issues we're going to talk about. So when you're writing in Haskell, you probably want to write most of your code as pure functions with no side effects. And all the code you write that way, it can't have race conditions, right? Because it doesn't modify objects that have already been created. So it won't corrupt some memory that another thread is trying to read. So that's ideal. But we can't write all of our code in pure functions because there's all these things that pure functions in Haskell can't do. So so different threads can't communicate using pure functions. Pure functions can't cause side effects. They can't get new information from the outside world after they start executing, right? They only have the function arguments, which get passed in when they start. Now, laziness, maybe adds an asterisk to that, but in any case, you're going to need some impure code to write a Haskell program. So let's look at how to structure that code when you've got multi-threads. And let's start by looking at threads in Haskell. Yeah, threads are a part of the GHC base package. Control concurrent, you can create one using fork IO. You pass fork IO and IO monad computation. And so fork IO will just start that computation running in a new thread, and that computation is unable to communicate with the rest of the program except by using side effects. You can kill the thread. If the thread throws an exception, it'll be killed. But other threads may not be killed, right? Whereas if in a single threaded Haskell program, an uncaught exception will crash the program. With threads, it's not that way. But what if that's not the behavior you want on exceptions? Right, maybe you want to propagate an unhandled exception from the thread you forked into the thread that forked the thread. And that's a pretty typical use case, and you can accomplish it using async. So async is a thin abstraction over threads. It's in the package async. Async provides a little more than what I'm focusing on here, because unlike threads, an async action, they're called, which is essentially a thread, but an async action can have a return value. But that's not why I'm interested in them here. I'm interested in them for this other feature that async actions, which are, again, threads, essentially, but like this wrapper over threads, they have this function link. So if you create an async action and you call link on it, then any unhandled exception thrown by that new task will propagate to the thread that created it, or the one where you called link. So that's handy for exceptions. Okay, now let's move on to structuring the code within your threads, right? The impure code that you're going to need. And let's start by looking at MVars, which I'm describing that as a type of synchronization variable. They could also be described as a type of mutex, and they help you to ensure things happen in the right order. So let's look at how that works. So MVar is short for mutable variable. They're in the GHC base package, control concurrent MVar. And yeah, it's essentially a variable where reading or writing it is an IO action. But what makes them kind of thread safe is you can't, reading and writing an MVar are mutually exclusive. So at any time, an MVar can be read because it has a value in it, or it can be written because it doesn't have a value in it, but never both at the same time, right? So an MVar is either readable or writable, but not both at any given time. Now, when you read an MVar, you actually take the value out of the MVar, and so then the MVar is empty. In other words, it's writable after you're done reading it. Now, if the MVar doesn't have a value in it, if it's not readable at the time you try to read it, then the thread where you're trying to read it will wait, it will block, until the MVar is readable, because it does have a value in it. And so if you have like multiple threads waiting to read an MVar, then right, only one of them can go at a time, right? They sort of queue up, right? So the MVar is empty, and there's multiple things waiting to read it. First time you write a value to it, one of those threads will get that value and unblock, and put the MVar back into a writable state while the other readers continue to wait. Writing is, just symmetrical with that, right? So if you have a writable MVar which has no value in it and you write to it, that succeeds immediately. It becomes readable. If you try to write to a non-empty MVar, which is therefore in a readable state, then your writing thread will block until it's in a writable state. And similarly, if you can have multiple writers queued up, right? Only one of them can go at a time. So this is just summing all that up. Yeah, so when you're using an MVar, you're alternating between reading, and writing, reading, and writing. Yeah. Now, here's some highlights of the MVar API. You can create an empty MVar. You can create an MVar with a value in it. Put MVar is the writing function that we just discussed, and take MVar is the reading function that we just discussed. Then there's also read MVar, which is kind of special. So it'll wait until the MVar is in a readable state, and then it'll return the value. But if there are any take MVars in the queue to read MVar will jump the queue. And if there are multiple read MVars waiting, they'll all receive the same value the next time the MVar is written to. And then read MVar will immediately write back whatever it wrote. And there's no chance for like anybody else to write to the MVar before that happens. So this read MVar is an atomic operation. Yeah, so that's kind of special. And then there are these various other MVar functions that I'm not going to spend much time on. They're kind of dangerous. They can lead to race conditions. But like, you know, for example, you can give a pure function and then read an MVar, apply the pure function to the value, and then write that back, the result of the pure function into the MVar. That's not atomic, so it can lead to race conditions. I'll try to unpack that more later. Okay, so let's talk about all the kinds of issues you can run into using MVars. So we can have deadlocks. So a deadlock is when you have multiple threads that are all blocked and none of them can unblock under any circumstances. MVars can cause that, right? So MVars cause threads to wait, and if your logic for the waiting isn't right, then you may get a deadlock. Right? You can get this kind of issue with any kind of mutex. MVars are a kind of mutex. So here's a simple example of an MVar deadlock. So we create an empty MVar, and then we try to read the MVar. There's nothing to read, so that's a deadlock. Or create an MVar with a value in it, try to write it. That's a deadlock. It's already full. Here's a slightly more complex example. We've created an empty MVar and then forked two threads. In one of them, we write to the MVar, and the other one we write to the MVar, and then here we read the MVar. So exactly one of these threads will deadlock. We don't know which one, right? Whichever one runs second will deadlock, because like one of these writes will be paired up with a read, but the other one won't, and so it'll block forever. Okay, so when does MVar code not have deadlocks? Here are some sufficient conditions for your MVar code to be deadlock-free. It might still be deadlock-free if these conditions aren't met, but you know, for some other reasons, right? Like essentially it boils down to one condition. Like these other conditions are like, you know, okay, like if you created it empty, you've got to write to it as your first action, right? And you've got to, for this condition, right, you've only got to use a restricted subset of the MVar API. But if those things are met, right, this is the key, right? The number of takes that you execute equals the number of puts you execute for each of the MVars. If that's true, then your MVar code didn't deadlock because each read was matched with a write and vice versa. Now, how can you tell if it did deadlock? Well, usually the runtime system will detect that it deadlocked. Your program will crash with this error. Other times it will just hang up. Other times it might work fine. You know, but yeah, if you get this error message, it's really unhelpful because it doesn't tell you where the issue is, right? Anywhere in your program that uses MVars could potentially be where the issue is if you get this error. So that can be really hard to debug. So like you really don't want to write MVar code with deadlocks. If you're writing MVar code, you want to be certain that it's deadlock-free before you ever execute it. So, right, and I said, okay, so if the number of reads equals the number of writes, and those other, you know, simpler conditions are met, then you should be good to go, but you can't just count the number of reads and writes because it depends on the causality within the program. So like it can be tricky to do this counting, but in some cases you can prove by this type of counting argument that it's not possible for a deadlock to occur. So here's an example that's going to come up again and again. So if two threads read and write an MVar an infinite number of times. Like one is like read, 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 and one is like write, 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 and they both just keep doing that for as long as the program is running. And that's the only way you're using the MVar, then it can't cause a deadlock, because each read will be matched with a write. So here's an example of that. So I'm using this function forever, which just creates an IO action that repeats this IO action infinitely many times. Here we're reading the MVar and then just printing out what's in it. In this other thread, we're going to put a number to the MVar an infinite number of times. Yeah, these threads will keep supplying the reads and writes they each respectively need. They'll keep on blocking. This program won't deadlock. So you can use MVars for sort of streaming data processing. You can have one or more producer threads which are writing to the MVar, and one or more consumer threads which are reading from the MVar. As long as the threads don't die and they keep reading and writing, they shouldn't deadlock. Your writes and reads should match up. So let's look at MVar race conditions. So like here's an example of an MVar race condition. This is from that example of a race condition I showed earlier, where you've got this variable x that starts as 1. We've got a thread that increments x, and we've got a thread that sets x to 3. So this program can illustrate like any of the scenarios that I mentioned previously. Like we can have the situation where this thread starts executing, reads x, and then this thread starts executing, sets x to 3, and then this thread sets x to 1 plus 1 equals 2. Or x can come out to 3, x can come out to 2, or like maybe the program executes before either of these threads run, could end up as 1. So that's a good example of a race condition. I talked about like modify MVar can lead to race conditions, and it's essentially for the same reason as we see here. When you modify an MVar, which is you read the MVar, you apply a pure function to the value, and then you write that result to the MVar, you can have this type of situation here, where first you read it, and then somebody else writes to it, and then you write your result that is now out of date. And I don't have time to go into all of this exactly, but there are other race conditions that are sort of variations on that theme. Yeah, here's my advice for using MVars. So don't update an MVar in a way where you're using the previous value of the MVar. So for this kind of race condition that I just described, right? So for example, don't use an MVar as a counter, because you can't increment an MVar without exposing yourself to race conditions. If you have a value of an MVar which depends on the value of another MVar, don't have circular dependencies. That can get really hard to reason about. And sort of generalizing off of this, right? Maybe don't read and write a single MVar in the same thread. And if you do need to do that kind of stuff, then TVars might fit the bill. But here's how I've used MVars, which I think is a good, safe way to use them, is the producer-consumer pattern, right? So you have one or more threads that are producers, they only write the MVar, and you have one or more consumer threads that are consumers, they only read the MVar. And you're not so likely to get deadlocks that way. You can rule them out if you do it right. Wouldn't use MVars unless you know exactly what you're doing with the MVars and why it doesn't deadlock, why it doesn't have race conditions. But let's look at less error-prone ways of doing concurrency. So software transactional memory. It works in these, like outside of the producer-consumer pattern. You can use STM, software transactional memory, much more generally. So an STM transaction is an atomic computation which reads and writes one or more STM variables. So an STM variable is a memory location, it holds some value. Unlike an MVar, it always holds a value, and you can read it instantaneously. So an STM transaction can read and write STM variables, it can do computations, And if the transaction completes, then all of its writes are executed. And if it doesn't complete, then none of its writes are executed. And if the variables which are inputs to the transaction, the ones that it reads, if they change while the transaction is running, then the transaction is restarted instead of completing. So that deals with like the issue we saw where you're trying to increment X and you read X and then your value is out of date and then you write X. That can't happen with STM transactions because before it does its writes, it will check if your input values are out of date and rerun itself if they are. So that helps to prevent race conditions. That's what I'm describing here. STM transactions normally don't deadlock because like they normally don't lead to waiting. But it is possible. Like if you have a really expensive computation trying to update an STM variable and its inputs keep changing faster than you can run that computation, then maybe that transaction will never complete and that might be a deadlock. So it is possible, but deadlocks are much less likely with STM than they are with MVars. So yeah, here's an example of STM. It's just the same example I've given before. What's different is that we can't have the final result X equals 2, because if we read X in thread A, and then set X to 3 in thread B, and then go to set X equals 2 in thread A, we're first going to notice, oh, X changed since I started running. So then we'll rerun and write X equals 4 instead. So let's look at how STM works in Haskell. So we have the STM package, the module control concurrent STM. We have TVars are the types representing STM variables. And we have a monad STM, which represents STM transactions. So all you can do in this STM monad is you can read and write transactional memory, and you can return a result. That's pretty much all you can do in an STM transaction. Here's some highlights of the API. You can create a TVar. You can run an STM transaction in the IO monad. And then here are like some functions that are helpful within STM transactions. Read TVar, right? Given a TVar, give me a transaction that reads it. Write TVar, given a TVar and a value, give me a transaction that writes it. And you know, you can build these up using do notations and so forth to build up your transactions. This retry function is interesting. If you hit that inside an STM transaction, then it's going to wait for the inputs to the transaction, right, the variables that you've read, to change, and then it'll restart the transaction. And that could lead to deadlocks, right? If the inputs to the transaction never ever change again in the run of the program, then retry will deadlock. Okay, so here's an example of a race condition using TVars. This is the same example as before, right? So incrementing X in one thread, setting X to 3 in another thread, but now using STM transactions, right? So this reading and writing is one atomic transaction. This writing is another transaction. And so like you can still get different results depending on which goes first, right? So maybe first you increment X and then X is 2, and then you run this and X is 3. Or perhaps they run in the other order, right? So now there's 2 possible results, but you can't get X equals 2, right? You can't have this update being interrupted in the middle and its result being invalidated. So that's essentially what STM gives us. Now, I think I'm gonna have to like, oh good. Yeah, this I'm gonna need to talk about. You can use TVars as for synchronization purposes, getting threads to do things at the right times, and it's pretty cool. So suppose you have a Boolean condition for whether your thread can continue or not, and you can compute that based on the value of any number of TVars. Well, then just in a transaction, test if that condition is true, and if it's false, then call retry. So then it will run again when the inputs have changed, check if the condition is met, and it won't continue until the condition is met. So that way you can use TVars to make a thread wait until the data it needs to continue is ready. Okay, So far we've talked about pure functions, MVars, and TVars as ways to write multi-threaded Haskell. We're going to look at composable streams. Right, the advice so far, write most of your code in pure functions, then all these problems we're looking at will not arise. And for the impure stuff that you'll need to have, try to structure your code to be deadlock-free and race-free. We've talked about some ways to do that. But streams are going to really help out for scaling this advice to more complex problems. Okay, so I'm talking about Streamly. And there are many other streaming libraries for Haskell, but I like this one, and this is what we're talking about. A stream is kind of like a list of IO actions. It's also kind of like an MVar, which is only written in one place. You can operate on streams using listy type combinators that make it really convenient to build up complex streams from simpler streams. Compared to MVars, streams have a really rich API, they're a lot more thread safe than MVars. It's less likely that you're going to screw up using streams than using MVars. Here's a picture of a simple Streamly stream. This is a ReaderT IO. That's a particular type of Streamly stream. So conceptually, here's what it consists of. You've got an IO action, which maybe hasn't been run yet, but if it runs, it will produce a result, and that result will consist of the first element of the stream, some value of type A, and then another IO action, which will give you the rest of the stream. So if that action is run, then, well, you might get nil, right, an empty stream, or you might get a result consisting of the second element of the stream, and then another IO action, which will contain the rest of the stream, so forth, so on and so forth. So Streamly has a few different types of streams. They're put into 3 categories and some subcategories depending on when the elements are computed, what order the consumer of the stream receives the elements, and what the semantics are for concatenating streams using the semigroup operation. So ReaderT, it's a lazy stream. The elements are delivered in the order in which the stream was constructed, right? So we have this cons m function for building streams, right? You can build streams the same way you build lists, and if you do that with a ReaderT, the consumer gets the elements in the order you wrote them. ReaderT and wReaderT differ in how concatenation of streams works. For ReaderT, first comes all the elements of the first stream, then all the elements of the second stream. Whereas wserial, when you concat streams, you get an interleaving of the elements of the streams. Yeah, I don't have time to really discuss all this in detail, but you can look at it, different types of streams. Streams are monad transformers. So like ReaderT, for example, right? All these stream types, they're monad transformers. So ReaderT IO is a monad. So it takes a monad as a parameter, right? So the idea is, right, you've got this monadic computation. If the monad is IO, then this part of the picture is, wrapping the result in IO, in the IO monad, but generally it's whichever monad you pass, right? Yeah, we've got, let's see. Yeah, I mentioned the stream concatenation, the semigroup instances. I'm gonna need to skip over some slides to get to the stuff I really want to talk about. But we've got various parts of the stream API here. You can build up streams like lists. You can get their head and tail like it was a list. You can map them. You can fold them. You can do all these things with monadic side effecting functions passed into your combinator. These are more listy combinators, Given a foldable such as a list, you can create a stream. So for example, if you have a list of A, you can create a stream of A using from foldable. And all of these stream types are interconvertible, right? So if you have one type of stream, a serial, an async, whatever, you can convert it into any other type of stream. And you can also run streams. So like mapm underscore, I'm going to use this later. We've got like a function that runs on each element of the stream, maybe has some side effects. You just run that function and discard the results. That's all mapm underscore does. So let's talk about like ways of putting together these pieces that I've presented to you to actually architect something interesting. So here's some design patterns. So you can create a stream using an MVar like this. Let's say you've got some action, right? Some action here. When you run it, it'll give you a foo as a side effect of IO, and potentially IO side effects, right? So let's try to make that into a stream. We'll create an empty MVar, and then we'll fork a thread, which will repeatedly run some action and put the result into the MVar. And then we return using the stream combinator repeat m, right? So we're going to return a stream which repeatedly executes this action. So that's a way to create a stream using an MVar. So when is that deadlock free? Well, some action always needs to return a value so that this stream is infinite, and you need to consume the whole infinite stream. So then your takes and puts will be matched up. So you can create a stream using an MVar. You can also create a TVar using a stream, sort of feeding the values of the stream into the TVar as they arrive. Or like more precisely here, I've got a function for taking a stream of V's and like a function for updating an A based on a B to create a TVar of A's. So here's the idea there, right? First, we're going to get the initial value of the TVar, and then we're going to make a stream scanning the stream of B's, right? So that'll give us a stream of A's by, right, we take the first element and the initial value of the TVar, combine those using F here to create the first value of the TVar, and then, right, we continue using those B's to update the A, to continue to update the TVar each time we get an element of the stream. We can also go the other direction. We can turn a TVar into a stream. Yeah, I'm not going to have time to like dissect this necessarily unless someone asks a question about it. But the basic idea is we check and see, did the TVar's value change? If it didn't, then we're going to retry our transaction. So this transaction is going to have the effect of waiting until the TVar's value changes. And then we put that value into the MVar so that it generates the next element of the stream we're creating here. So now putting these things together, this is sort of the crux of what I wanted to say. You know, I talked about like with MVars, you don't want circular dependencies between them. Like you don't want MVar A to depend on the value of MVar B and vice versa. You could run into deadlocks or race conditions. And so like this is one way to have sort of conceptually circular dependencies in your state that is being used by multiple concurrent processes, threads. There's a way to do it using streams and MVars and TVars. So the scenario we're looking at here, you've got some updates streaming in from the outside world, like let's say an API, and you've got the state of your application. So the state is going to be updated by the updates, and updates to the state will generate actions which have to be sent to the outside world. But also, we have to update the state to reflect the results of those actions that we know beforehand are going to happen. Like before those results actually come in via updates, we want to update the state instantaneously based on the stuff we did. Right, so like for example, if this was like a banking application, right, you'd like to decrease the user's balance based on a purchase they made before that transaction actually clears. That would be an example of how this, what an arrow in this direction could do. So that's the scenario here. And unfortunately, it looks like I'm not going to have time to dissect exactly how this works. But this is a way of putting together all these pieces in a way that has some really nice properties that are described on subsequent slides. So you've got, right, your function to apply an update to update the state, right, an update coming in from outside. And you've got your state as STM, and you've got your ability to compute actions from a state and then to apply those actions to a state. This will put them all together in a way that'll work depending on stuff, right? So there are these various issues that you could run into, and I've described conditions under which you won't run into them, and I've described limitations of this approach, ways that those limitations could potentially be addressed. I would love to talk about this larger code example, but I'm out of time. This is about like merging many concurrent streams together into one stream. That's what's shown there. So I'm ready to take your questions now. Thanks for coming to my talk. Curious to hear what people have to say. So I see some questions here, but I think they're going to be read out to me by Courtney.
Yeah, I'm going to go ahead and do that. But first, thank you so much, Morgan. We appreciate you giving us that talk. And even though it sounds like you could have talked for a lot longer, maybe next year. Or maybe we need the Streamly library talk too. But, you know, we could talk about that. So the first question that we had was regarding any other languages and their runtimes. I don't think you addressed that. Is that something you can address now?
Does this so parts of this talk apply to other languages and their runtimes, like sort of the stuff about like avoiding deadlocks and race conditions. A lot of that is not really specific to Haskell. Like the same reasoning could apply in other contexts if you had other abstractions that have the same rules. Does that answer that question?
I think it was just a does this talk apply question. So I believe so. But if Alex, if you have additional, like a follow-up, please feel free for that. Our next question says, thank you, M for mutable, but also for mutex. I think that was more of a comment.
Yeah.
So I'm gonna mark that one as answered. So the last question that we have currently is, as somebody who has never heard of Streamly, but has of conduit and pipes, could you please compare Streamly to the other two?
Yeah, unfortunately, I can't make that comparison because I haven't used conduit or pipes. Sorry about that.
All right. So maybe somebody over in Discord is more aware of that, but I've not heard of conduit or pipes either. So if anybody else has any questions, throw them in quick. But otherwise, I think, Morgan, thank you so much for coming today and for being here and giving this talk.
Well, thank you all for coming and giving me the opportunity to talk. I wonder, like, is there anything that I sort of breezed through that people would be interested to see more detail on?
Here, let me turn on chat for a second. That might help. There we go. Chat is open if anybody has any immediate questions. Oh, we have a thanks for a fantastic talk.
Okay. Yeah, I would love to share the slides with you. Oh, now that the chat is enabled, I can do that.
And I will also attach the slides to the YouTube video when that goes up.
Excellent. So, like, it is sort of related to like these comments about back pressure here, but that's specific to like this scenario. So I'm going to try to talk more generally about that. So like with Streamly, you can do parallelized maps. Like for example, you can use the parallelity stream type where it will like try to compute multiple elements of the stream at the same time. You can run a map on that in a way where the map can run in parallel on different elements at the same time. Yeah, Streamly is definitely designed for that type of use case. And it is somewhat related to this code example. So we've got, in this example, we're using the Hacker News API, and we've got an API function to get a story, and then to get all of the comments associated with the story, and we want to get all of the stories on the front page and all of the comments associated with them. So like the intent of this code is it's gonna fork out a bunch of API calls that all run at the same time, and then computations on those, like get story here, get comment. These are simple computations in this case, yeah. Like this code, which I've just shown a simplified version here without MVars, it's going to fork out a bunch of threads that will make a bunch of API calls, and those threads will all be waiting on each other, but only waiting on the things that they actually depend on, and then all of it will get merged into one result at the end. Maybe that speaks to your question. Sweet.
Great. All right. Well, hey, and Morgan, is it possible for us to also get the link to that GitHub code that you're looking at so we can make sure that we use it to accompany the video? That would be great.
Yes, I will post both these things in Discord as soon as we get off here.
Awesome. Well, everybody, thank you for joining us. Morgan, thank you for the talk on this library, and hopefully it will be useful to many, many, many people. Thank you very much.